Hello everybody. In the last class we had gone through the discussion on DC motors, and we almost completed the discussion on the DC motors. Towards the end of the session, we just very briefly discussed on how we go about performing the dynamic model of the DC motor. In this session we shall carry that through, that is, make a dynamic model of the DC motor which will complete our discussion on the DC motor, and then we shall take up a new topic, and that is on 3-phase systems. So, first the DC motor. So, we have been studying quite at length about the DC motor. We are familiar with the symbology. We have the armature, and to the armature is attached the brushes through the commutator, and we have two non-idealities in the dynamic case. One is RA and the other is LA. RA is the winding equivalent winding resistance of the armature. LA is the equivalent inductive reactance of the armature. Now, this is the DC motor which has a mechanical shaft, and we said that in the case of the motor the energy is moving from the electrical domain to the mechanical domain, and the mechanical loading gets reflected on the electrical domain as back EMF across the brushes. Now, we apply a voltage EA, and there is a armature current IA which is flowing through it. This is RA and LA, and then in the mechanical domain we have a torque Tg which is getting generated, and because of the torque Tg there is a speed, angular speed of rotation omega in radians per second, or speed n in RPM, which gets generated. Now, this is on the mechanical domain. Now, this mechanical domain also contains its own load, or the reflected inertia J, which is like the mass of a vehicle, or the mass of the load, or a mass of a very big wheel which has an inertia to it, and then when it is rotating it gets stored in the kinetic form, and that is called the inertial energy, which is stored by virtue of an object being in motion, which we know that it is stored in the kinetic energy form, and therefore, J, or the inertial parameter, is similar to L, the inductive parameter, and therefore, the state variable in the case of the mechanical domain which is involved with the parameter J would be omega, the speed. There could also be at the bearings some friction associated, and we will call it as a friction B. Now, this is the electrical domain, and this on the right side we have the mechanical domain. The link between the electrical and the magnetic domain is the motor. There is a back EMF, we said, and this back EMF can be expressed in terms of the mechanical domain parameter or mechanical domain state variable, and that is K phi omega. We saw this in an earlier discussion. So, that is equal to the back EMF. The torque component here the torque that is generated can be related to the state variable on the electrical side by the same k what we have written phi I A. Now, as we are doing dynamic model, we do not want to take the RMS values, let us take the instantaneous values. So, therefore, I will replace these by the instantaneous values. So, we have EA, we have IA and EB. So, this is the relationship. Now, we can apply the Kirchhoff's voltage law to the electrical domain here. You see that the applied voltage is EA, there is a voltage drop RA, there will be a drop across the LA inductor, and then of course, there is a drop that gets developed across the brushes because of the rotation of the armature, that is the generated EMF or the back EMF, and that is called EB. So, therefore, we can apply the Kirchhoff's voltage law in this area, in this electrical area. Likewise, on the mechanical area, the mechanical side also, one can apply equivalent to the Kirchhoff's voltage law, the potentials or the potential variable being torque. The speed is common, like the current being common in the electrical circuit, the speed is common to all the things connected to the shaft of the armature. The sum of the potentials, which means in this case the torque, should be equal to 0 like the Kirchhoff's voltage law. So, the generated torque is Tg, should supply J d omega by dt and also b omega, and if there is any other load torque, that component also. Okay. So, we are applying the Kirchhoff's voltage law on both the electrical domain and the mechanical domain with the state variables, which are the state variables. On the electrical domain, we have one dynamic element LA with associated state variable IA, and then we have J as another dynamic variable in the mechanical domain, which is the reflected inertia, and then the associated state variable omega. So, we have two state variables at this point. Now, there is one more issue, and that is phi. How are we generating phi? Because the excitation, the field is being generated differently with respect to different topologies of the motor, as we saw in the case of the shunt motor, the series motor, compound motor, the phi is being generated separately. So, which means as far as this motor is concerned, there is one more input which is phi that we need to take care. So, first let us consider the case of the shunt motor, where phi is a constant, or a separately excited motor where phi is a constant, we are not touching phi. So, under that condition, we can now write the equations. Now, the electrical domain side first. So, we have LA dIA by dt. So, the voltage across that is EA minus RA, EA minus IA RA minus EB, but EB can be expressed in terms of the state variable, which is given by k phi omega. So, which is EA minus k minus IA RA minus k phi omega. So, for the moment we are considering phi as a constant, that is this. Let us take this, copy. So, we go to the next page. Yes. So, now on the mechanical side there is a generated torque Tg. Now, this is going to supply the inertial component d omega by dt, which is similar to L di by dt, plus I R A equivalent to the resistive drop is B omega in the mechanical domain. Now, plus any other load torque, any other load torque which may be applied to the mechanical shaft. All this should be generated by Tg. So, J d omega by dt will be equal to Tg. Now, Tg can be expressed as k phi I A in terms of the state variables k phi I A minus B omega minus T load. So, as a mechanical input to the system there is T load, and as electrical input to the system we have E A. So, combining these two we have d I A by dt equals, look at this, E A by L A, R A by L A into I A, and k phi by L A into omega. So, I will rewrite it as minus R A by L A into I A minus k phi by L A into omega plus 1 by L A into E A. So, this is one equation. Then we have d omega by dt, which is the mechanical equation. So, we have for the state variable I A k phi by j, k phi by j into I A minus B by j into omega minus 1 by j into T load. This is the second equation, that is, this equation has been rewritten in this form. These two equations completely define the dynamics of the motor. Now, if it is a separately excited motor or a shunt motor, where we can assume phi to be a constant, then we can write it in the standard form of I A dot d phi by dt omega dot d omega by dt, which is equal to minus R A by L A minus k by L A k by j, k phi by j, this is, and minus B by j, I A and omega being the state variables in the state vector, plus 1 by L A minus 1 by j, sorry, 0 and minus 1 by j, because and then we have two inputs E A and T load. So, this is of the form x dot is equal to A x plus B u, the standard form. Now, if phi is not a shunt, but let us say a series motor, in that case phi itself is a function of I A. So, which means here phi becomes proportional to I A, which results in, let us say this becomes now K 1 I A, K 1 I A. So, we do not, because there is no state multiplication, I A into omega, I A into I A, this is I A square, this is a non-linear system. Therefore, we do not put it in the standard matrix form, we just leave it as differential equation system. So, that would become a non-linear system, but still that would give you the entire dynamic model of the DC motor system. So, the phi should appropriately be modified, whether it is a constant or whether it is now a function of I A or so or any other variables, that should automatically be put in there, and that will give you the complete dynamic model of the DC motor in the state space form or differential equation form. Okay. So, with that we conclude our discussion on DC motors. The DC generators and DC motors are a class by themselves. They both are similar machines, similar in structure, but the only difference being that in the case of the DC generator, the energy being input on the mechanical domain, you are taking out the energy in the electrical domain, and therefore, from the electrical domain point of view, it is a generator. And in the case of the DC motor, you are applying the energy input in the electrical domain and taking out the energy in the mechanical domain. But constructionally, both the machines are very similar, and a DC generator can be operated as a DC motor and DC motor as a DC generator, vice versa. Internally inside the machine, inside the armature, the currents that are flowing in the coil are always AC, but only by means of the device called the commutator, which we have discussed, and the brush combination. External to the motor in the electrical circuit or external to the generator in the electrical circuit, the signals are DC. Otherwise, within the motor, it is always an AC signal. Now, the idea, the concept of energy being passed through many domains is the underlying principle in which most of the machines, most of the applications are being used. Many of the applications, for example, the induction motor or in the case of the alternators for generators, are a combination of all these domains. And most of the, in the electrical technology, the central, what do you call, the central concept or the central theme is some prime mover, propulsion, movement on the mechanical domain, and the electrical domain is just the currents and the potentials. The core of the transformation of the energy from one domain to the other is always, most of the cases in this set of equipments, being done in the magnetic domain. So, the central cauldron is generally a magnetic domain. Most of our electrical technology applications, magnetic domain. So, you could get power or energy input from the electrical domain, take out power in electrical domain, you could take out the power in mechanical domain, or you can put energy into the magnetic domain from the mechanical domain and take out power into the electrical domain. All these are possible. So, the central mechanism which makes possible the conversion between many of these domains is the magnetic domain in the case of most of the electrical equipments. And all these area, including the interfaces between the electrical, magnetic, and within the magnetic, they are always AC. And in many applications, it is not single phase AC, it is 3-phase AC. So, before we try to understand and learn about the equipments, electrical equipments which fall into these categories like the induction motor, the synchronous motor and generators, 3-phase transformers, they all fall into the category of this multi-domain principle. In the case of 3-phase transformer, of course, this domain is not there. There is only, that is, the mechanical domain is not there. There is only electrical transformation between electrical and the magnetic domains. In the case of the induction motor with shorted rotors, you have only one electric domain which is inputting, and this other electrical domain is not there, and you have the mechanical domain. In case of the wound rotor, where you have the rotor windings not shorted, taken out to a resistor, set of resistors, then you have the input electrical domain and output electrical domain, you also have the mechanical domain, so on and so forth. So, like that you can have many combinations, but all falling into this class of or this type of concept. So, before we go further at all into the understanding of these equipments like the induction motors, 3-phase transformers, synchronous motors, synchronous generators, we should have a good understanding of 3-phase systems and what is this 3-phase systems. So, the major part of this session is going to now deal with 3-phase systems. This is also written as 3-phi for 3-phase system. So, in the literature you will see that phi being used for the term phase. So, now what is this 3-phase system? How does it look like, and what is its character, and what are its features? Let me take a source, a sinusoidal voltage source. Let me arrange it in this fashion. So, let me say that this source is connected to a resistive load. Let me connect it to a resistive load as shown like this. So, this resistive load R is connected across this source, which has 2 terminals here, and let me name the terminal A, and let me name this terminal as N1, and the voltage across these two EAN1. Okay. So, this is the voltage, and there is going to be a current through this one, and we will call that one as IA. Now, I will put one more source, and let me connect it in this fashion. Electrically, they do not have anything in common, except that I am putting one within the other, and that is also having the same resistor R, and let me call those terminals as B and N2, and this is EBN2, which also has a potential like that, and it has a current IB, which takes this path along this resistor to N2 back again to the other terminal of the source. That is also an AC source. Now, I put one more, the third. So, I have one more source which is going to also be supplying a load resistance R, and that is also not going to be electrically connected to the other two sources, and it has two terminals, which I am going to name it as C and N3, and the voltage source itself is named between the terminals, given the terminal names EC and 3, and there is going to be a voltage and a current IC. So, you see there are three sources, they are not at all linked electrically, they are absolutely independent of each other, each of them supplying their own loads, Now, suppose let us apply some constraints. So, what are the constraints? Let us make the amplitudes of the voltages same for all the three. So, what is the first constraint? We make not the instantaneous, mind you, we are making the peak amplitudes or peak values of the sine waves of each of these AC sources, sinusoidal sources, same for all three, that is EA N1, this is 1, EA N1 peak will be equal to EB N2 peak will be equal to EC N3 peak. The peak values of all the three sinusoids will be the same, that is the first constraint. And then of course, we have made are the impedances of all the three as resistive and all three are same. The loads that all the three see are the same. Now, we apply the second constraint. Each of the sources have a phase shift with respect to other of 120 degrees phase shift with respect to each other. Each of these sinusoidal sources has a phase shift of 120 degrees with respect to each other. That is the second and the most important constraint that we are going to apply. So, if such a thing is applied, what happens to the phasor diagram? You see, now let me have E A N 1, RMS value of the EAN1 source is being taken as the reference. Okay. Now, let another voltage, and let me call it, let us say EBN2 lag EAN1. Note that the RMS amplitude is the same because the peaks are same, the RMS is the same, is lagging by 120 degrees. The EB source voltage is lagging the EA source voltage by 120 degrees. And now, let me have the EC source voltage ECN3 lagging EA source voltage by 240 degrees. Then the second constraint gets established. What does the second constraint say? It says there should be a 120 degrees phase shift with respect to each other, that is all these three sources. So, we have 120 degrees phase shift between EAN and VBN, 240 degrees phase shift between EAN and ECN on the negative side, but this means that ECN is leading EAN by 120 degrees, and between EB and EC, because it is 240 with respect to AN and 120 with respect to EAN for EB, this becomes also 120. So, you see that EC is 120 degrees displaced from EA and 120 degrees displaced from EB. EB is 120 degrees displaced by EC and 120 degrees displaced with respect to EN. This satisfies the second condition. The first condition, of course, being the amplitudes are all same, the phasor amplitudes, and the second condition is they are equally displaced with respect to each other in a circle, and that is 120 degrees, 360 by 3, which is 120 degrees with respect to each other. So, this is the second constraint. Now, this is the nature of the sinusoids that will be applied. So, which means that though electrically they are not connected, we have applied a constraint on the three source voltages, which is equal in amplitude, equal in effective amplitudes or the peak amplitudes, and the second is the phase displacement between each other should be equal, and which is 120 degrees. This also implies that we have the effective values of all three equal, the peak and the effective values. So, now we can make some conclusions here. Now, all the written paths of all these things can be clubbed together, because there is nothing here in this, no other component which comes, just plain wires, conductors. So, let us say we remove all these conductors and club them together like this. And join them. So, what have we done? The 6 wire system has now become 1, 2, 3 and a 4 wire system. From a 6 wire system, it has been reduced and made more compact into a 4 wire system, and of course, IA, IB, IC is going to flow here. IA plus IB plus IC will flow here. Now, there are two things that we need to have a look at. That is the voltage waveforms and the current waveforms. How do they look like, and what is the instantaneous values of these 3 put together, and what is the current resultant current which flows through this line, the return path line, and this line is called the neutral. This is called the neutral line. The return path line, which is common, is called the neutral line through which IA plus IB plus IC flows. If the loads R all are balanced, the voltages are all as according to the constraint, equal effective values, 120 degrees phase shifted, then you will see that IA plus IB plus IC is equal to 0 and not a very large value. So, which means the conductor here need not be very thick. In fact, if it is equal to 0, one can just eliminate this conductor. One can just eliminate this conductor and make it a 3 wire system. You see, a 6 wire system became a 4 wire system, and from the 4 wire system, because of the applied constraints and loads being balanced and equal, you have IA plus IB plus IC is equal to 0 at every instant of time. So, it is equivalent to having no wire here, and you can just make it into a simple 3 wire system. Now, let us have a look. Let us as such not erase this line, let this continue to be there. We shall erase it after some time, after we just make some study on the currents and the voltages. So, now let us have a look at the voltages here. So, we draw the 3 phase voltages E, A, now we start from 0, this is the time t. Now, E A is the reference, so let it start from 0 like that, the sinusoid, and then reaches 1 full cycle. Now, the E B is displaced 120 degrees, it is lagging E A by 120 degrees. So, this was E A N 1. So, this is 90. So, 120 will be somewhere around here. So, we have a waveform which goes like that, completes its cycle. This is 120 degrees lagging, and that is E B N 2. Now, if we join all the things N 1, N 2 and N 3 become same, and we can say that all these are now same and it is equal to N, node N, and we can erase this and then say that these are C N, B N, A N. Then we have the third, the C waveform, which is a 240. This is around 270, and therefore 240 will be around somewhere here. This is a 240 degrees, and so on. We have sine wave which continues. So, this is E C N 3, and because we have commoned the return paths, it is now E A N, E B N, E C N. It is a 4 wire system. Now, this will get projected like that, and this will continues like that. The cycle repeats. So, now if we look at these waveforms, one thing that we observe is that at any section, you can take any section. At any section, this is positive, the other two are negative, and here these two are positive and the other one is negative maximum. So, there will always be a cancelling, and you will see that any section the sum will be equal to 0. Let us say if this point this is having a value which is half. So, the red one, which is the ECN, is having half, let us say normalized value. Green one is minus half. So, minus half plus minus half is 1. This is 100% peak. So, they both cancel and becomes 0. Likewise, let us say at this point it is plus half and plus half, blue is plus half, green is plus half, red is minus 1, gets cancelled, becomes 0. Likewise, every point you will see that the addition of all these three becomes 0, and as they are passed through resistive loads, what is IA? This waveform will be also similar to IA. IA IB and IC will also have similar, only the amplitudes get changed by the factor of R, because all are having R's. So, EAN by R IA, EBN by R is IB, ECN by R is IC. So, they also will have similar. So, you will see that every instant of time IA plus IB plus IC is equal to 0, and this means, but this will happen only if R's are same, balanced loads and the voltages are same. So, this means that this wire is redundant, and you can now remove that wire here. So, we have a strange connection between these two, which is written in this fashion. So, let us say I have 3 loads, 3 sources, and I have 3 loads which are written in this form R, R, R. Now, all the 3 sources, the written path points I am going to common them, call n, and in the case of the loads also, all this are going to be commoned, and then the other ends of the sources are connected in this fashion to the loads. So, this is a 3-phase, 3-wire system. Now, look at the way the source and the loads are connected, and we saw that EAN, EBN, ECN had a phasor diagram which was EAN, EBN, ECN. Okay, 120 degrees, this is 120, 120, 120 degrees with respect to each other, all having equal amplitude. Same. Now, this can also be written differently in this form, because we can take anything as the reference. Okay. 120, 120, 120. Okay. So, you have EAN, EBN, ECN, or you can also write it in this form, EAN, EBN, ECN, all 120 degrees out of phase. So, in the literature you will see that they use these 2 ways of writing the phasor diagrams for the 3-phase circuits. And the circuits are also built such a way that it tries to give you a better feel, that is along the vectors, that is what was supposed to be the vectors. Let us say we have the 3 vectors here. The circuits are written along these vectors to give a better feel, and this common point is called N. So, we have the A phase circuit, let us say, connected to we have the A phase circuit connected to the A phase load or the A phase resistor R. So, this is EAN, and then we have the EBN, the B phase circuit, which is connected to the B phase load. So, let me connect this. To the B phase load, and then we have the ECN, the C phase source, which is connected to the C phase load R. So, you see that this is much more aesthetically pleasing and gives an idea that they are all 120 degrees phase shifted with respect to each other in a phasor manner, both the load and the source. So, in the literature you will find this as a pretty common way of expressing 3 phase circuits, and by the way it looks, there are 2 indications. One is that this looks like a star, and sometimes this is called a star circuit. Star load is also in the star form, and if it is in the inverted way, that is, if in some cases the circuits may be written in this form. Here the A, B, C. So, this looks like a Y, and this is called a Y circuit. So, for this type of circuits where you have one end of the sources or the loads connected, joined together, common, and the other 3 terminals are taken out and used for connection to the source or the load, then such a connection is called star or Y connection. So, this is a star or a Y connected circuit. Now, some terminologies are in order. This is called the phase. Let us have a, so let me have a load of this form, which I am writing here. So, this is a star circuit or a Y circuit, as it may be called conveniently. So, let us say this is point A, this is point B, this is point C. So, A, B, C's are connected to a 3-phase load. A, B, C are connected to a 3-phase source. Now, the voltage across each of the phase, and let me call this one as N of the neutral, across each of the phase, that is, this is called line, this is called line A, this is called line B, and this is called line C. Line A, line B, line C. Between the line and the neutral is called the phase, and this portion is called the phase circuit. The phase circuit and the voltage across A and N is called the phase voltage. Likewise, the voltage across B and N is called the phase voltage EBN, and the voltage between C and N is called the phase voltage ECN. These are all phase voltages. Now, the voltage EAB is called the line voltage. EBC is line voltage, ECA is also line voltage. So, EAB between the lines, EBC, ECA, they are all called line voltages. The current going through the A to N phase, let us say, this is called the phase current, and the current flowing in the lines are called the line currents. So, you have the line currents and the phase currents. So, current flowing through the phase circuit is the phase current, current flowing through the line is the line current. Of course, in this case the phase current and the line current are the same. The voltage across the lines is called the line voltage, the voltage across the phase circuit is called the phase voltage. Now, there is one more way in which the circuit, the load or the source can be connected between the lines. So, let us say I have line A, line B and line C, and we saw that we connect it with respect to the phasor diagram in this manner, in the manner of a star, but it can also be connected between these terminals as shown here. Like this, R, R, R. So, this type of circuit looks like a delta, the Greek letter delta, and the lines can be connected as shown like this. So, here also the voltage across the phase circuit is called the phase voltage. In this case, phase voltage, line voltage is the same. The current, you have the line currents which are flowing in the lines, phase currents which are flowing in the phases here. Let us say this is the phase currents, line currents, phase voltage, so on. So, in general we have two major types of circuits. You have the star circuit and delta circuit. So, in the literature, star circuit is also called as Y circuit. So, in all the three phase systems, you either have the star circuit or the delta circuit. We shall discuss more about this in the next class. Thank you for now.